Now we introduce another way to prove logical equivalence. So before we had used truth tables, and truth tables are very reliable because you can just check essentially every possible case. But there are other ways to do stuff, and today we look at a different one, which is sort of like proving logical equivalences by rewriting. So the idea is to replace one expression with another expression that has the same truth value. And we can do this step by step using known logical rules. And so this video is about some of these logical rules, or the basic logical rules that you can use, which will help you prove equivalences. So of course, the first idea is that you could sit down and prove each one of these logical rules themselves by using truth tables, and then you can use them to do other proofs, sort of like an algebra of logic. So let's start with the first rule we'll start here is implication. And so what implication says is that P implies Q is equivalent to not P or Q, right? And the advantage of this is that you can sort of get rid of implications and end up with just not and an or. And we'll see that this will be quite useful because it's much easier to operate with these nots and ors than to think about implication. The second rule is biconditional. And so biconditional says that P, if and only if Q, is equivalent to P implies Q and Q implies P, right? And so the idea is that when you have a biconditional, you can break it into two implications. And now we have the implication rule where you can break it into nots and ors, which means that everything that has a biconditional and implication, you can ultimately break it down to nots, ors, and ands, and there just operate with nots, ors, and ands, right? Okay, so to then operate with these nots, ors, and ands, a very useful rule is called De Morgan's rule, and it essentially gives you a way of distributing sort of the not when you have an expression of the form P and Q or P or Q. And maybe the way to remember this is that when the negation goes inside, the operator changes. So the idea is that this negation, or the way I visualize it, is as if this negation were entering and distributing, but now this operator here, so this is the and, becomes an or, and so you get not P and Q is equivalent to not P or not Q. And same for the how do you say, for the or actually. So a not P or Q, so again the negation goes inside and the or swaps to an and so you get not P and not Q. Then another useful rule is double negation, which is not P is equivalent to P. And so this is just saying that if you negate twice, you get the same thing, which makes sense. I mean, you can always write down the truth table for this, but it makes sense. If you have truth and you negate it, you get false, and then you get it again, you get truth, so you get the same thing, and same for false. If you negate it, you get truth, and if you negate it again, you get false, right? The next rule is called contradiction, and so contradiction states that P and not P must always be false. So, in other words, a statement and its negation cannot both be true at the same time. Because remember, and is only true when both of them are true. And you can't have that something is true and not that is also true. So this always has to be false. And finally, you have a rule called tautology, which is that if you have a statement P or not P, then that should always be true. Because again, the or is true when at least one of them is true, and it must be that either P or not P is true. So if P is true, then of course this is true, and if P is false, then not P is true, and so this will be true, right? And so the main idea is that you can essentially prove all of these using the truth tables. And once you've done that, you can sort of use these as like an algebra, and we'll show an example in a different video. You can use this as sort of like algebra operations to do an algebra of logic and be able to show other expressions, right? So instead of checking every row in the truth table, we essentially are manipulating the expressions algebraically.